Okay. Now, in the previous lecture, we stated Burnside's lemma, which is the following. So, given a finite set, let's say Y, and a subgroup G of the symmetry group Sy of Y, then recall that fix of pi is the set of all elements that are fixed by the permutation pi. And the cardinality of fix of pi is clearly the number of cycles of length 1 in permutation pi, right? Now, the lemma says that if y mod g denote the set of orbits of g. Okay, so what is the orbit of a group acting on a set? Let's say y. So when you look at the the G equivalent classes, right? So when you have the group acting on the set, you get a partition into equivalence classes because the G equivalence is an equivalence relation, and these equivalence classes are called the orbits. Okay, so the elements which are taken by the action of a group, like if I take one element, it is going to a subset of the elements, and these subsets form an equivalence class, and that is an orbit. And so we get this orbit. So if y mod g denotes the set of orbits of g, then the number of orbits is given by the formula 1 by the order of g, summation over all permutations in g, cardinality of the fix of pi. So the average number of elements of y fixed by the permutations in G is actually equal to the number of orbits of G, acting on the set Y. Okay, so that is Burnside's lemma. Now let's see how to let us look at an example. So let's say that Y is a set 1, 2, 3, 4, and G is is the group with the identity 1, 2, 3, and 4. Then 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. Right? J and G dash is the group again with identity 1, 2, then 3 and 4. Then 1 by itself, 2 itself, 3, 4, then 1, 2, and 3, 4. So as abstract groups, they are isomorphic. Both are isomorphic to Z2 cross Z2. But as you can see, as we observed earlier, the action will be different because the cycle structures are different. So the number of orbits of G is given by 1 by 4. The cardinality of G is 4. Times look at the the elements fixed by each of these. You will see that you will get 4 plus 0 plus 0 plus 0, right, for the action of G. And on the other hand, the number of orbits of G dash is 1 by 4 into 4 plus 2 plus 2 plus 0, because in the cycles 3 comma like 1 2 1 comma 2 3 and 4, the two elements are fixed. Then 1 2 3 comma 4, two elements are fixed again, right? And therefore I get 4 plus 2 plus 2, right? Of course, identity fixes all the elements, which is 4. So the number of orbits of G and G dash are different. For example, in the case of G, you get only one orbit, and in the case of G dash, you get two orbits. Okay. Now let us try to prove Burnside's lemma. Now, for any element of Y, let us look at the set of all permutations which fix Y, right? So which is called the stabilizer subgroup of G, denoted by G sub Y. Okay, so G sub Y is the set of all permutations that are that fix the element y, right? So pi dot y is equal to y. Then to calculate this sum, right? 1 by mod g summation pi belongs to the cardinality of x pi. So let us try to sum over all elements of g cardinality of x pi, right? Now what is this? So this is sum over all permutations. Sum over all the elements in y, right? So so you want to count, right? We count the elements in y, just that pi dot y is equal to y, right? That is precisely the cardinality of fixed pi, right? So the elements which are fixed by pi, right? That cardinality can be obtained by summation y belongs to y, where pi is fixing y 1, right? So this will be the same. But now I can change the order because I can as well count for each element how many permutations fix this. So I can write it as summation y belongs to y, summation overall permutations in G, where y is fixed by pi. Right? So again, but what is this, right? So what is this term, right? Now that is precisely the number of elements, right? Or number of permutations which fix the element y, right? Which is cardinality of gy. Right? So which is the stabilizer subgroup, right? So summation overall y belongs to y, cardinality of gy. Now let us see. Can we look at cardinality of gy in another way, right? So when we look at the action of the group, the elements in the orbit, let's say gy. So I denote by gy the orbit of y, right? Because so what are basically the orbits? So so if I take an element and look at all the other elements to which this element is mapped by elements of G. So this form the orbit of Y. Right? So therefore, it makes sense to denote it by G Y or G dot Y. So now, so elements in the orbit Gy of Y occurs the same number of times in the multiset pi dot y, set of all permutations pi dot y for pi in G. So why is that? Because so how do you prove this? So if you have the following three easy results, like two left cosets are either equal or disjoint, this is something I asked you to go through or prove. Then another easy result that we can show is that two orbits are either the same or disjoint. Okay. Now the number of left cosets of a subgroup, right, is the cardinality of the orbit of y, right? So stabilizer of gy is the cardinality of the orbit of y. How many elements are there in the orbit? That is the number of left cosets of the subgroup gy. Now, if you prove these three, it will be immediately clear that the elements in the orbit occurs exactly cardinality of gy times. So this will give you the identity that the cardinality of gy is actually equal to the number of elements in G by the number of elements in the orbit of y. Okay. So, so once you have this, we can just substitute. So we get 1 by order of g summation fixed pi is equal to 1 by order of g summation y belongs to y, which and it was g sub y, cardinality of g sub y, but that is equal to order of g by order of gy, right? Now what is this? So we can cancel order of g because that is fixed. So therefore I get summation 1 by order of g dot y. Now how many times this particular term occurs in this sum, right? So for every element in the orbit of y, right? So the corresponding term will be 1 by cardinality of gy, because elements in the orbit stay together, right? Under the action of the group, the elements in that orbit are taken to the other elements in the same orbit. It doesn't go out of it. So therefore, you will see that exactly the number of elements in the orbit, that many times the term 1 by cardinality of gy occurs. So which means that the contribution of each orbit will be exactly 1, right? Because each orbit has exactly that many elements. That many times this term 1 by order of gy comes. So therefore, this is actually counting the number of orbits. The contribution of each orbit is exactly 1. So therefore, it counts the number of orbits in the action of g on y. So that is what we wanted to prove, right? The cardinality of y mod g is actually equal to 1 by cardinality of g summation fixed y, right? Cardinality of so so that is the Burnside's lemma. Okay. So now, yeah, so here I think I need to write the cardinality of y. Okay, yeah. So that is the Burnside's lemma. Now let us look at an example. So let us look at the 6th cycle, let us say H, which for hexagons or something, right? 6th cycle H, whose vertices we want to color using n colors. So you are looking at a regular hexagon where all the sides are equal. So so that there is a symmetry. Okay. Now, so we want to color the vertices using a set of n colors. Now, we say that two colorings are same if one can be obtained from the other by rotation, right? So if I can just rotate the regular or hexagon so that the colorings remain in the position, and then I rotate it, then I get other colorings, right? So these colorings are all considered equivalent, right? Basically, I don't distinguish between coloring obtained by just the rotation of this object. Now, how many inequivalent colorings are there under this? How do you use this? So we want to find the cardinality of fixed phi, and then we get the formula, right? So let us look at the set of all colorings of the hexagon using, let's say, n colors, right? So we look at the set of all colorings. That is our set y, right? We are going to apply the group action on this coloring. So G be the group of permutations of C that permute the color cyclically. So basically the rotations, right? So we can see that since there are 6 vertices, you have exactly 6 rotations, including the identity, right? And you will see that this is actually isomorphic to Z6. Now, of course, these permutations, the rotation, so the subgroup of all rotations can be generated by a single element. You just rotate once, and then that rotation you can apply that to itself again. So if you take this single rotation forward, like one going 2, 2 going to 3, etc., right? And you apply it again and again. Like for example, if it is sigma, then sigma square, sigma cube, etc., you will get all the elements in the group. So it is generated by the single element. Okay, something that we need to we will use maybe. So now let us look at a coloring of the vertices, right? So let's say R G Y B B Y B B W, right? So red, green, yellow, blue, and white. Now once I rotate this, what happens? I can get, for example, red going to green, green going to yellow, yellow going to blue, blue going to blue, and blue going to white, and white going to red, right? So I will get WRG, YBB. Similarly, I get BWR, GYB, etc. by rotations. So I can rotate and get this kind of colorings, right? Where I assume that one is now given the color W, right? After this one rotation, I will get one will be given the color W, right? So W goes here, and similarly red goes to 2, etc. Okay, now the orbits of the group G correspond to the equivalent coloring, right? So we want to count the number of orbits because we want the inequivalent coloring, right? So all the elements in the same orbit are basically equivalent. So what we are seeing here is that these colorings are all equivalent, right? Because this is actually obtained from this by just rotation. This can be obtained by rotation, etc. Therefore, elements in this orbit of this coloring are all equivalent. So we want to find how many such orbits are there so that we will get the number of inequivalent color. Now, what is that? So the cardinality of the orbit of the action of G on C is mod C mod G, the cardinality of C mod G, which by Burnside's lemma is 1 by order of G, summation over all the permutations in G, cardinality of fix of pi, right? Now, if sigma is a generator of the group G, we have the following cases, right? So we have either identity, sigma square, right? Sigma cube, sigma raised to 3, sigma raised to 4, sigma raised to 5, etc. Right? So these are the generators. So let us look at each case. Now, if you are looking at the identity of G, then all the colorings are fixed by pi, right? Because it doesn't do anything, so everything is fixed. So all the n raised to 6 colorings, because for every vertex I have n choices. So all the n raised 6 colorings of the hexagon are all fixed by pi, right? The identity. So the identity permutation is written like this: 1, 2, 3, 4, 5, and 6. Each one is a cycle. Now, on the other hand, suppose we have the generator, let's say sigma, right? So which is the rotation by ones: 1, 2, 3, 1 going to 2, 2 going to 3, 3 going to 4, 4 going to 5, and 5 going to 6, and 6 going to 1, right? So if sigma is the generator, then which kind of coloring sigma fixes, right? See, because it is rotating, the colors in the cyclic fashion, the two colorings are equal only if all the colors are the same, because the colorings basically move around in circle, right? And if I want these two colorings to be the same, I want all the colors in each of the vertex to be the same. Now, if each vertex gets the same color, then since I have n colors, I have n different colorings possible, right? Where all the vertices get the same color. So sigma, for example, right, gives exactly n such colorings. Now, what if you look at the sigma inverse, which is the rotation in the backward rotation, right? So 1 going to 6, 6 going to 5, 5 going to 4, 4 going to 3, and 3 going to 2, and 2 going to 1, right? So that sigma inverse, again, the same, right? So if I just rotate by 1 all the way backwards, again, I want all the vertices getting the same color, otherwise the coloring will not be fixed by pi. So for each of these two, I get n such coloring, right? Now, what if pi is sigma square or sigma raised to 4? Then what are these permutations? If sigma is this, then you can verify that sigma square is this permutation, 1, 3, 5, and 2, 4, 6. Right? Now, what is this permutation like? For example, right? 1 going to 3, 3 going to 5, and 5 going to 1, right? Similarly, 2 going to 4, 4 going to 6, and 6 going to 2. Right? So, because sigma square, or in our case, is of this form, if the colorings of these alternate elements, right, are the same, right, then such colorings are fixed by pi, because if I move twice, I just need to get the same color, right? And similarly, for each element, if it moves exactly twice, right, in forward, then that color is the same, then the coloring is okay. So therefore, such colorings will be all fixed by sigma square. But how many are there? Well, I can choose any two colorings for the first two elements. Then we know that the remaining must be all based on this. So therefore, I have n into n square possible colorings, and in n square of these colorings, this sigma square will be fixing each of them. And similarly, sigma raised to 4, which is 153 and 264, will also be fixing such coloring, right? So therefore, n square colorings will be fixed by sigma square and sigma raised to 4, right, each. Now, if pi is sigma cube, then sigma cube is precisely 1, 4, 2, 5, and 3, 6. Therefore, the colorings of the form, like the first three are the same, right? Then, no, first three is fixed. Once you fix the first three, then the remaining three are the same, right? So therefore, I have three choices, right? N into n into n cube colorings are there. And these n cube colorings will be fixed by permutations of the form sigma cube, right? Permutation sigma cube. So this covers all possible elements, right? All the 6 elements in the group. So therefore, we can now apply Burnside's lemma, right? So let us do 1 by 6 into, right? 1 by 6 into n raised to 6 colorings fixed by the identity, n raised to 3 coloring fixed by sigma cube, right? Then n square coloring fixed by each of sigma square and sigma raised to 4, and n coloring fixed by each of sigma and sigma inverse, right? So this is the number of inequivalent colorings. So if we are using exactly n colors, we get this. If I am using only one color, what you will get? 1 plus 1 plus 2 plus 2 by 6, which is 1. Right? And for 2, you will see whatever it is. So this is something that we can do, right, by using Burnside's lemma. But now let us observe something else. Okay. So if you look at if you look at this this count, right, that we have obtained here, we have 1 by 6 into, right, n raised to 6 plus n raised to 3 plus 2n square plus 2n. So let us see what is the exponent of n raised to 6 here. So n raised to 6 comes from the identity of G, and you will see that the identity has exactly 6 cycles in its cycle representation, right? So the identity permutation has exactly 6 cycles, 6 1 cycles. Right? Now, what about this 2n, right? So the exponent of n is 1, right? Now, how many cycles are there? For example, in sigma, right? Sigma has only one cycle, right? Which is with all the 6 elements, there is one cycle. Sigma inverse also has only one. So you will see that the number of cycles in sigma here, for example, is the exponent of n here, right, in the count. For each permutation, you can verify that it is the case. For example, when you are looking at sigma square or sigma raised to 4, sigma square has two cycles. So the exponent is 2 for n, right, n raised to 2. Sigma raised to 4 also exactly the same. And sigma cube has exactly 3 cycles, 1, 2, 2, 5, and 3, 6. And therefore, we have exactly sigma, n cube, right? N cube colorings. Now, why is this? Can you see why? This is something which is kind of easy once you think about it. Because let us say that you're looking at a permutation, and this permutation fixes some colorings, right? Now, if a permutation is fixing the colorings, then look at any cycle of the permutation, right? So if I look at a cycle of the permutation, when you look at the the permutation as the product of cycles. So take any factor, right, which is a cycle. All the elements in this cycle is precisely rotating, right, like by one step, or it forms a cyclic rotation, right. Now, if I have this rotation will be in this cyclic rotation will fix a coloring only if all the elements, that corresponding elements which appear in the rotation, get the same color. So if 1, 3, and 5 are all getting the same color only, the rotation of 1, 3, 5, 1 going to 3, 3 going to 5, and 5 going to 1 will be also preserving the fixing the color, right? So therefore, the permutation will fix the color only if all elements in that particular cycle, right, will get the same color. So therefore, this has exactly n choices because I am using n colors. Now look at the second cycle. The second cycle also the same thing, right? Because all the elements in that cycle must be getting the same color. So again, it has n choices. So that is why the number of cycles determines the power of n, right? Exponent of n. So now it is clear, right? So we can even write it as a theorem now. Okay, so we will go to that. Before that, let me set a homework. The vertices of a 5 cycle, let's say C, is to be colored using K colors, right? Find the number of inequivalent colorings if rotations and reflections of colorings are considered equivalent. Okay, so and once you do this formula, again find the value when K is equal to 7. So that is a homework. Now, this is something that we already observed, that if you look at an uncoloring of a finite set X under the action of a group G of the symmetries of X, right? So then the coloring, any coloring is fixed by a permutation, fixed permutation pi, only if all the elements of a cycle of pi get the same color, right? Something we observe. So therefore, the cardinality of fix of pi, right, is precisely n raised to C of pi, where C of pi, is the number of cycles in pi, right? So therefore, by Burnside's lemma, right, we can rewrite, this observation and as follows, right? So if G a group of symmetries of a finite set X, and you are looking at the number of G inequivalent n colorings, right, of the set X, that is given by 1 by cardinality of G, summation pi belongs to G, n raised to C of pi, where C of pi denotes the number of cycles of pi, right? So the proof, I already explained the proof, so I want you to write it down formally, with all the necessary arguments. Okay, so that is the homework for you. Now, so here is a remark. So like if you want to get the the number of colorings with some additional information, like for example, we want to count with respect to the number of occurrences of each color, right? So I want to say that I want to count the number of colorings, G inequivalent colorings, where the red color appears 3 times, blue appears 5 times, and green appears 7 times, etc. Right? So I can do that also. Right? This is something which we can do if you put it into use the observation that we had in the previous this result, that using the cycle structure of the permutations, we can count this, right? So if you include that also into the formula, then we should be able to clearly tell how many inequivalent colorings are there, where each each coloring each color occurs a specified number of times, right? Now this becomes even more clear when you observe that the permutations, right? The action is by the group G, which is a subset of the symmetric group Sx. So basically, the action is by permutations, right? So now the permutations of a coloring. Suppose I take a coloring and permute them. Whatever your permutation is, it is not going to change the number of times a given color appears, right? So if I look at a coloring and I permute, permute the elements, then I am going to get another coloring where the number of colors of, number of times each color occurs is precisely the same. So the set of all colorings is now can be divided into based on the number of times each color occurs, and that will be like, so the action of the group will be any subgroup that we are looking at, right, will be always restricted to each of these subclasses, right, of the coloring. So with that observation, we should be able to gain more insights. So that is what we are going to prove in Polias theorem. So so continuing our observation. So let us write the cycle type of a permutation as the n tuple. So we are looking at permutations of n elements, let's say. Then the cycle type of permutation is the type of let's say pi is the n tuple C1, C2, etc. Cn, where Ct is the number of cycles of length t in pi. So this could be like, Ci's could be zeros, right? It is always a non-negative integer, and you can look at some example.